Huh. Hello. I'll be right back. I'm gonna take an aspirin, I think. Hello. Buenos días. Waiting for a few more people. I guess while I'm waiting, I will show off my wares. Uh, Yesterday, my uh, my parents were visiting, and all right, thanks for letting me know. Um, so my parents were visiting. They left this morning, and so yesterday I was like, I wanted my parents to try foraging with me, and so we foraged, and I made this, and this has got to be the best handle I've made. That's a walnut handle. It's been oiled, and the pins are good. So that's a nice knife. I had already made the metal part of this knife, but I put the handles on, and then I made this one from scratch, and my dad made one too. So that actually meant a lot to me because my dad usually won't do anything he doesn't want to do. Um, and he actually forged, so that was kind of cool. All right. Let's see. Do I have a? I have 14 people, 16 people. Okay, so that means I can get started. 58,000 comments. Wow. Okay. Hello, everyone. So we are done with. We're finished with forces. So we're moving on to energy. Okay. Um, so we'll be spending the next, I don't know, 3 or 4 lessons learning about energy at a higher level than we did last time. So the first type of energy that I want to talk about is kinetic energy. Um, Kinetic energy is denoted by K, and it is 1/2 mv squared. Now there's a property of kinetic energy that's going to be useful for this lesson, and it's the following. Because mass is positive, and when you square something that's positive, the kinetic energy always has to be greater than or equal to 0. Okay? Because its mass is positive and the square of a number is positive. So it's always got to be greater than or equal to 0. If it equals 0, that means you are at rest. And so for this reason, kinetic energy is often called the energy of motion. Okay? So that's one form of energy. The other form of energy is potential energy. Okay. And potential energy is energy due to your position or due to your configuration. Okay. So potential energy is denoted by U. Okay. And because it's an energy of position, we put U of x. So this is like f of x because x is our variable for position. So we're going to say U of x for energy as a function of position. Now, by the way, kinetic energy does not depend on position. It depends on velocity. So we could say k of v if we wanted to. Okay. So the key equation for today is that potential energy is related to force via the force is minus the derivative of the potential energy with respect to position. Okay? So this is a key equation for today. This is a key equation as well, but it's kind of an equation from last year, but I'll still box it in. One important thing is this is a definition. You guys ever use a three-prong equal sign? This is a definition. So the force is the derivative of the potential energy function. So if you happen to find a u of x such that when you take the derivative, it spits out the force, then you found a potential energy function. Okay? So it's a definition. It's just if you find a function that satisfies this relationship, then you found the potential energy function. Okay? So there's no magic to it. It's just you find that function and you have it. Okay? The total energy is denoted by E, and it is equal to K plus U. So kinetic energy plus potential energy is the total energy. So I'm going to prove a theorem for you guys. And that theorem is that energy is conserved. Okay? So what does it mean to be conserved? It means that the value of the total energy is not changing as time goes on. Okay? Another way of saying that that something is not changing as time goes on is saying that its derivative with respect to time is equal to 0. Okay? So that's what we're going to prove. We're going to prove that the derivative of the energy with respect to time is 0. Okay, and this is one of my favorite proofs. So I remember the first time I read this proof, I was like, that's cool. So I hope you also find it cool. This is going to involve calculus, so if you are just taking calculus for the first time, this probably won't make sense to you yet. Watch it once you learn about derivatives. This is not something that I'm going to ask you on the exam, okay? So this is just kind of for fun, this next section right here. So let's prove it. So energy is kinetic energy plus potential energy. Okay. And so that means that the derivative of the energy with respect to time is the derivative of the kinetic energy with respect to time plus the derivative of the potential energy with respect to time. Okay? So let's go ahead and do these derivatives. Okay? What is the derivative of the potential energy with respect to time? Well, notice that potential energy is a function of x. But I'm taking the derivative with respect to time. So this is a situation where you want to apply the chain rule. Okay? So I'm going to apply the chain rule. The derivative of the potential with respect to time is going to be the derivative of the potential with respect to x times the derivative of x with respect to time. That's the chain rule. Okay? Now, the derivative of position with respect to time is velocity, by definition. And the derivative of potential energy with respect to position, well, by definition, that is going to be negative the force. Okay? So, in the next line here, I can write du dt as negative FV. Okay? Negative force times velocity. So now let's do the derivative of the kinetic energy with respect to time. All right? Well, the kinetic energy is a function of velocity. It depends on how fast you're going, not where you are. So when we do the chain rule for the kinetic energy, so we're going to do the chain rule for kinetic energy. So that's going to be dk dv, because kinetic energy is a function of velocity, times dv dt. So again, an application of the chain rule, but with a different variable because kinetic energy is a function of a different variable. dv dt is the acceleration. What's the derivative of the kinetic energy with respect to velocity? Well, looking at 1/2 mv squared, when we take the derivative of v squared, that's 2v. The 2 cancels out the 1/2, and we just get the derivative of kinetic energy with respect to velocity is mv. The derivative of kinetic energy with respect to velocity is momentum. That's strange. That's not an accident. All right. So, MVA. So now I'm going to plug that in. MVA. Now you can see that the first term has V, and the second term has V. So I can factor out V, and I get V times M times A minus force. Okay? But according to Newton's second law, F equals ma. So therefore, ma minus F equals 0. So we have the derivative of energy with respect to time is 0. Notice how the key, in order for energy to be conserved, Newton's second law has to be true. Okay? So when we're talking about classical physics, which is the subject of this class, classical physics, energy is conserved because of Newton's second law. So Newton's laws are more fundamental than energy. You don't get energy conservation unless you have Newton's second law, because that's the key step, is going from here to here. Another thing I want to say is that the energy is simply a function that was constructed that has 0 derivative. So sometimes people attach almost a magical significance to energy, And really, it's just a combination of variables such that when you take the derivative of them with respect to time, you get 0. Okay? So there's nothing more to it than that. So I hope you enjoyed that proof because it's one of my favorites, and I think it really shows how cool energy is. Okay. I didn't see that in high school. I saw it in college. So aren't you guys lucky you get to see the proof that energy is conserved in high school? Okay. So now we're going to get to the main subject for today, which is U of X graphs. So a common thing to do is to graph the potential energy as a function of where you are. Okay, so maybe your potential energy function looks like this. I don't know. I'm going to make this bump a little bit bigger. Okay? So there's your potential energy as a function of x. By the way, energy is measured in joules. I should probably say that. So basically, if you're at this location, you have this much potential energy. That's what that means. Okay? Now, how do we interpret this? Well, we use the fact that force is minus du dx. So what if we put the particle at this location? Okay? If we put the particle at that location, well, we can see that at that location, the slope is positive. So, by the way, du dx is the slope. So really the force is minus the slope. Okay? So if the slope is positive, then minus the slope is negative. So the particle is going to get pushed to the left. All right? What if the particle is here at this location? Well, here the slope is negative. All right? So that means that a negative number is positive, so that means that the force is positive. What if the particle is right here at this location? Here, the slope is negative, or is positive, excuse me, so the force is negative. And here, the slope is negative, so the force is positive. Okay? So, a really useful way to visualize what direction the force is going to be going in is to think about a ball on a hill. Think about this potential energy graph as a hill, and think about which way a ball would roll if you put it here. Okay? So if you put the ball here, obviously it's going to start rolling to the left. All right? If you put a ball right here, obviously it's going to roll to the right. If you put a ball right here, obviously it's going to roll to the left. If you put a ball right here, obviously it's going to roll to the right. Now here's my question for you. What would happen if I put a ball right here? Okay? What would happen if I put a ball right here? What would happen if I put a ball right here? So what is happening at these locations? What's going to be the force on the particle at those locations? Type it into the live chat if you know the answer. Man, I just got a headache all of a sudden. Oh my gosh. Will anyone answer? Will anyone dare to answer? 0. Excellent. So because this is flat, the slope is 0, so there's no force. So these are basically the equilibria. So the maxima and the minima are equilibriums. Equilibria. Okay? Oh, I want to write that down for a sec. Write down that other useful thing. It is useful to think of ball on the hill when looking at these graphs, okay? Okay, the maxima and the minima are equilibria. But here's the thing. You actually have two types of equilibria, okay? You have this type of equilibrium and you have this type of equilibrium. Now, what would happen if you put a ball right here? It has to balance perfectly, okay? What would happen if you had a ball right there and you nudged it a little bit to the right? What's going to happen is it's going to roll away from that equilibrium and it's going to end up over here. What would happen if you nudged it and you nudged it to the left? It's going to roll away and never come back. So this type of equilibrium right here, where a small nudge leads to a bigger nudge that pushes it away from equilibrium, that's called an unstable equilibrium. Okay? So basically the maxima are unstable. The minima, however, if you pushed the ball right here to the right, it's going to start rolling back and forth like this. If you push the ball to the left, it's going to start rolling back and forth. So for a minimum, if it starts out near the minimum and you push it, you nudge it, it stays close to the minimum. Actually, it undergoes simple harmonic motion about the equilibrium point. Shh. So the minima are called stable equilibria. So you have stable and unstable equilibria. Okay? Now, let's think about let's think about the total energy, which is constant. All right? If the potential energy goes up, the kinetic energy goes down. All right? If the potential energy goes up, the kinetic energy goes down. So, but here's the thing. As we discussed on the previous page, because kinetic energy has a square in it, it's always greater than or equal to 0. So the potential energy can only go so far before the kinetic energy drops to 0. All right? So for example, and actually you can never have, you cannot have U greater than the total amount of energy. Why not? So for example, let's pick potential energy equals 10, but total energy equals 5, for example. Then you would have 5 equals K plus 10, which means that the kinetic energy is negative 5 joules. By the way, the units of energy are joules. And this is a big no-no. Okay? So you cannot have the potential energy greater than the total amount of energy. So let's suppose I have a U of x graph that is very simple. It looks like this, just a parabola, for example. Okay? I can draw a horizontal line representing the total amount of energy. Okay? Now we have to have the potential energy less than the total energy. Okay? So what that means is that, for example, anywhere beyond this location, the particle cannot go. Yes, you can have kinetic energy less than or greater than the total energy. That would mean you have negative potential energy, which is possible. Okay. So basically, these regions of the x-axis where the potential energy is greater than the total energy are forbidden. You can never go there. So those places exist, but you can't get to those places with your current amount of energy. Okay? So you're stuck in this region. This is the region where you're stuck. Okay? So you can actually get some kind of interesting situations here. So what if my potential energy graph looks like this? And for clarity, I'm not drawing the axes just so that we can be really clear cut. What if this is your total amount of energy? Okay. What if that is your total amount of energy? Well, in that case, you are stuck to one of two regions. You're either stuck here or you are stuck here. Okay? But you can't go between the two because you don't have enough energy. What if you had this amount of energy? E2. Then you could go, so this is scenario 1. For scenario 2, you could go anywhere in this region. Okay? What if you had an amount of energy E3? In case 3, you're stuck to a very tiny region like right here. Okay? So you have regions where you can go, and you have regions where you can't go. Negative potential energy typically means that an object is bound or stuck to a certain location. We'll talk more about that later on in the class. Okay? So depending on how much energy the particle has, that determines where it can go. All right? Another thing I want to point out is that according to the definition of energy, kinetic energy is total energy minus potential energy. So actually the difference between these two lines, that represents the amount of kinetic energy. So that represents the amount of kinetic energy. All right, so these regions where the particle can't go with the amount of energy it has are called forbidden regions. And forbidden regions in classical physics, you can never go to the forbidden regions in classical physics. But it turns out that the universe is not 100% described by classical mechanics. It's a more accurate theory of nature is the theory of quantum mechanics. And quantum mechanics actually has something really interesting that can occur. In quantum mechanics, a particle can temporarily go into a forbidden region and show up on the other side. That's really cool. Okay? A particle can go through the forbidden region temporarily. It can't stay there, so you'll never find a particle in the forbidden region just at rest. But it can continue through to the other side of the forbidden region. And when that happens, it's called tunneling. So tunneling is the thing that is not possible in classical mechanics, which is the subject of this class. But if you go on to take physics in college, you might take quantum mechanics, where you learn a more accurate theory. And you learn that elementary particles like electrons and so on can actually tunnel. Okay? And so that's really cool. Now, I want to tell you about something that I find to be really trippy, which is we could think about this graph as the potential energy. And what if x is not position of a particle, but what if x is the configuration of the universe? Okay? The universe is described by quantum mechanics. Most accurately described by quantum mechanics. Okay? And, you could imagine a situation where, what if the potential energy of the universe looks like this? Okay? And we're sitting here in this configuration of the universe. What would happen if the universe tunneled, quantum mechanically tunneled, to a different equilibrium? That would mean that the universe as we know it would cease to exist. We wouldn't even experience such an event, because we would just stop existing and the universe would tunnel to a new configuration that has different stuff going on. Okay? This is a real possibility. The universe could tunnel to a different equilibrium, which would destroy the universe as we know it and create it in a different form. This is something that scientists actually think about. You don't need to be scared, because the universe has not tunneled for the last 13 billion years, so the probability that it tunnels in the next 100 years is pretty small. But the probability is non-zero. You could even think about the Big Bang. It's possible that the Big Bang was not really the beginning of the universe, but really the moment when the universe tunneled to the current equilibrium that we're in. So it's kind of interesting. The other thing I want to talk about is I want to draw a special U of x graph. It looks like this. Like that, and it just keeps going. So here, x is representing the distance from a nucleus. Distance from a nucleus, okay? And let's suppose that you have an alpha particle with this amount of energy, okay? Do you guys know what an alpha particle is? An alpha particle is a helium nucleus, okay? So a helium nucleus has 2 protons and 2 neutrons. Protons have positive charge. This other nucleus has a positive charge, okay? This other nucleus has a positive charge, and as you know from electricity, opposites attract, likes repel. So this alpha particle is going to approach the nucleus, and then it's going to hit the turning point here. This is called the turning point, and it's going to get bounced back. Okay? So this is electrical repulsion. Because of that. Okay? Now, you could imagine a situation where the alpha particle has this much energy, in which case it has enough energy to move over the top of the hump. And once it moves over to the top of the hump, you get a new force takes over. It's called the strong nuclear force. okay, the strong nuclear force, and that force is going to pull the alpha particle all the way into the nucleus, right? If you have a ball that's right here, it's going to roll all the way down, okay? And so basically, if the alpha has enough energy, okay, it will fuse to the nucleus. So this is how fusion works. Fusion can be understood with U of X graphs, okay? So you have to give the alpha particle enough energy to get over this hump so that the strong nuclear force can pull it in, okay? Now, how does the alpha particle get that much energy? It has to be hot, high temperatures. So this is why fusion occurs in the center of the sun. It's because in the center of the sun, it's hot enough where random alpha particles have enough kinetic energy to make it into the nucleus. If you try to have cold fusion, then the alpha particles are going to approach the nucleus and then get repelled electrically. Okay? Actually, what happens is, this is sort of a simplification. Actually, what truly happens is, even at high temperatures, it still doesn't have enough energy to enter the nucleus, but it's close enough that it tunnels through. So actually, fusion happens because of tunneling. The alpha particle approaches, it gets close enough, and then it tunnels into the nucleus and stays there. So I think that's really nifty. This is why we cannot have fusion at room temperature. It has to always be at extremely high temperatures so that you have enough energy to give it a chance to tunnel through the barrier. Okay? So this is how fusion works. All right, so that's my lesson for today. So I will see you in the Zoom room. Okay? Bye for now.